Hello everybody, welcome to our second lesson of electronic devices. In this lesson, I'm going to introduce you to silicon doping and how it enhances the conductivity of silicon. I am also going to introduce you to two types of silicon doped material, an N-type and a P-type doped silicon material. This lesson is also going to be theory intensive, so you better wire up your brain for the new information I'm going to bombard you with. Without further ado, let's get started with the lesson. Silicon doping. Silicon doping to modify or enhance its conductivity. Silicon doping just means that we are adding impurities to the silicon. That's all. To the silicon crystal. That's all. You know what doping means. You must know by now. So, silicon doping is just adding impurities or adding substances to the pure silicon. If you remember, in the previous video, we saw how silicon conducts current. Even though we showed that silicon conducts current, but it only conducts a very small current, and this is not desirable for applications. We want our silicon to conduct a lot of current. So what do we do to increase its conductivity? So the question is, what can we do to increase its conductivity? It seems reasonable. It seems reasonable from what we have learned so far from the previous video that in order to increase the conductivity of the silicon, we just need to add more electrons in the conduction band, because the conductivity of a material depends on the existence of electrons in the conduction band. So if we can increase the number of electrons in the conduction band, we can increase the current, we can increase the conductivity of that material. So it turns out we can do this, the increasing of electrons in the conduction band, by adding impurities. By adding impurities, this process is known as doping to the pure silicon crystal. And if you still remember, a pure silicon crystal is also called an intrinsic silicon. You should know that by now. If we add impurities to the pure silicon crystal, we form an impure silicon crystal, which is called an intrinsic silicon crystal. Moving on to the next page. Now I'm going to introduce you to the N-type doped silicon crystal. In this type of doping, we add more electrons to the conduction band. In the other type of doping, which is called P-type doping, we add holes. We add holes in the silicon atoms. The adding of holes also increases the conductivity of the silicon crystal. Not only is the conductivity of the silicon crystal increased by adding electrons in the conduction band, but it turns out it is also increased by creating more holes. And this makes sense because If there are more holes, it means that there's a path for the electrons through which they can move through the holes, jumping from one hole of an atom to the other, which is some sort of current as well. So now for the n-type doped silicon, its theory depends on covalent bonding. So it would be very helpful if you knew something about covalent bonding. So to increase the conduction electrons, we will add a material whose valence electrons, this impurity material, must have its valence electrons being greater than that of silicon, so that during the covalent bonding, all the 4 atoms of the silicon are bonded to the other 4 atoms of this impurity atom, so that we leave one excess electron which does not have a bonding partner. Because it does not have a bonding partner, this excess electron is forced out of the bonding. It is no longer part of the bonding, so it moves into the what? Into the conduction band, which then increases the density of electrons in that. The movement of it into the conduction band increases the number of electrons in the conduction band, which also increases the conductivity of the silicon. Do you get it, guys? I hope you do. This, remember, is for an n-type doped silicon. We add an impurity whose valence electrons are greater than that of silicon, and this usually this impurity material is a pentavalent atom. It has pentavalent atoms, meaning that the valence electrons of its atoms are 5. Penta meaning 5. The valence electrons of its atoms are 5. So you add a substance to the silicon whose valence electrons are 5, so that the other 4 from the impurity bond with the other 4 of the silicon, so that one is left, and the one that is left is no longer part of the bonding, so it is forced to move into the conduction band, where it will constitute as a current if we apply a potential. I mean a voltage or a potential, whatever you want to call it. Moving on. This type of doped silicon is called an n-type because we have added more negative charges in the conduction band, or electrons, and we know electrons have a negative charge. Now, so let's take a closer look at the covalent bonding of silicon atoms and the impurity atoms. In front of you, I have drawn 4 silicon atoms. We have 4 silicon atoms, 1, 2, 3, 4, and in the middle of those 4 silicon atoms, we have the impurity atom. And in this case, the impurity atom is phosphorus. Phosphorus, as you can see in front of you, has 5 valence electrons. 1, 2, 3, 4, 5. But the silicon has only 1, 2, 3, 4. So during bonding, if you know covalent bonding, where the bonding occurs between pairs of electrons, you should know this from your chemistry class. You know that just because we have 4 silicon atoms, 4 silicon valence electrons and 5 phosphorus valence electrons, the 4 from the silicon and the 4 from the phosphorus will bond together, but this let's pick this one. Let's assume that this one has no bonding partner. This one will be forced, it's this one. It will be forced to move into the conduction band. As you can see, the other four have bonding partners. As you can see, 1, 2, 1, 2, 1, 2, 1, 2. And each one of these, the four are from the silicon, one silicon atom, and the other four are from the phosphorus atom. And the fifth one from the phosphorus is moved into the conduction band because it has no bonding partner. This is the excess electron becoming a conduction electron because it does not have a bonding partner and it is no longer part of the bonding process. So I hope you get this, guys. If you have some background on covalent bonding, I think you will be able to understand. But if you don't, just take a look at what covalent bonding is and you will understand. Moving on, guys. Now, let's look, instead of looking at these silicon atoms, this one, I mean the silicon atoms and the impurity atoms, it's complicated. So let's just look at a simplified representation of that silicon doped crystal whose conductivity now has been enhanced by the presence of free electrons in the conduction band. As you can see, this is a silicon crystal. We assume this is our silicon crystal. It's just a solid crystal with impurities, a phosphorus impurity inside, and the placement or the mixing of the silicon crystal with the phosphorus has caused the conduction electron density to increase, as you see in front of you. Now, just because of doping, the free electrons in the conduction band have increased. This is just a simplified representation. We want to avoid all those messy electrons. It's tiring to draw the electrons and show how they are bonded, and the diagram becomes unclear at the end of the day. Moving on, guys. Now we are going to look at a p-type doped silicon crystal. A p-type silicon crystal is different from an n-type doped silicon crystal in that for a p-type, we create the conductivity of the silicon crystal is increased by introducing holes to the atomic structure of the silicon instead of adding electrons to the atomic structure or the molecular structure of the silicon. As you have seen, for an n-type, we add more electrons. For an n-type, we are adding more electrons. But for a p-type, we are creating more holes in the atomic structure of the silicon, and these holes are created by addition of an impurity to the silicon crystal. We wouldn't be able to create these holes if there was no impurity within the crystal. But remember, for a pure silicon crystal, remember this, guys, for a pure silicon crystal, the holes are minimum, as well as the electrons in the conduction band are minimum. But once we dope the two, once we dope the silicon crystal, the holes are increased by p-type doping. For n-type doping, the electrons are increased. I hope you get it. Now continuing, moving on. As I've already said, in this type of doping, I wrote bonding. It's doping. It's supposed to be doping. 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 I meant doping. In this type of doping, we add an impurity material whose valence electrons are less than that of silicon. Can you see the difference from the n-type? For the n-type, we added a material whose valence electrons were greater than that of silicon. But for a p-type, we add a material or an impurity whose valence electrons are less than that of the silicon. So that during bonding, we do this. I even give you a reason why we do this. So that during bonding, one electron, not one electrons, one electron licks a bonding partner, not part, but a partner, thus creating a hole. Boron and gallium, whatever the name is, gallium, are some of the examples of these doping, of these impurities. These ones, they have trivalent atoms, meaning that their valence electrons are 3, and we know that the valence of electrons of silicon are 4, and indeed the valence electrons of boron are less than that of what? Of silicon. So that during bonding, the 3 from the boron will bond covalently with the other 3 from the what? From the silicon, but a hole will be left because the other one from silicon will have no bonding partner. You understand? From the boron, because the boron only has 3 valence electrons. Moving on. Now, taking a closer look again at the covalent bonding of silicon with boron. Boron, as I've said, it's a trivalent atom, meaning it has 3 valence electrons at its outermost orbital. As you can see, I've even drawn the silicon atom as well as the boron atom. As you can see, the silicon atom has 4 valence electrons, and the boron, as the name suggests, as this name suggests, has 3 valence electrons. So during the covalent bonding, what will happen? This one will pair up with this one, and this one will pair up with this one, and this one will pair up with this one, but this one will have no one to pair up with, so a hole from there will be left. You understand? There is the hole. There is the hole. As we can see, our poor silicon electron, this one, has no bonding partner from what? From the boron. All the other ones have found their bonding partner. So now we have a hole, and this hole is what creates or what increases the conductivity of the silicon crystal. Moving on. A simplified representation of a p-type silicon crystal. So this is our silicon crystal. Assume it's a solid. It's a silicon solid. It's a silicon solid with impurities, and that impurity just happened to be what? Boron, so that we form a p-type material. So just because it contains the boron impurity, the number of holes in the silicon crystal have now increased, and this increase in holes increases the conductivity of the silicon. And yeah, I think that's all, guys. That is it. Let's see if we have some. Yeah, now let's compare a pure silicon crystal to a doped silicon crystal. It may be a p-type, an n-type, but for this case I've drawn only for an n-type. This is an n-type doped silicon crystal, because for an n-type the conductivity is increased by increasing the density of the what? Of the conduction electrons. These are electrons, guys. There's a negative sign encircled, meaning it's an electron. And as you can see, for a pure silicon crystal, which is at a temperature above the absolute zero, some conduction electrons exist, but they are not a lot. So the conduction of the conduction of silicon will not be huge compared to this one. Here, in this one, for the n-type doped silicon crystal, this one will be more conductive than this one, because in this one we have more conduction electrons than in this one. Can you see? The same thing goes for what? For a p-type doped silicon crystal. That's it for this lesson, guys. I hope you have enjoyed the lesson, and if you have any questions, please leave them below in the comment section, and I will see you next time in the next video. And please don't forget to give this video a like, and please subscribe. I really need your help. I want this channel to grow, so please consider subscribing and liking this video so that I can be able to produce more educational videos like these ones. Thank you.